3rd of March, and we are continuing our conversation in Chapter 5. We're talking about turbines. I'm specifically going to work problem 546. I'm talking about the way a turbine works, or anything that generates electricity. Now, anyway, so anything in nuclear, all that nuclear really does is it just creates enough heat to cause water to flash into steam. And then the steam, because it has a greater volume and a less dense situation, will spin something similar to this and make it work. Same with coal, same with natural gas. Now, solar energy works differently. Solar energy has no moving parts, which is really a huge advantage in my opinion. But solar energy is different. Solar works using what's called the photoelectric effect. And basically, I'm giving you a short course in something that you could study for 7 years, so we're not ready to go out and build solar panels at this point. But basically what happens is you have panels that are set up that they're basically like semiconductors, and they call it doping, but you dope the solar cells with this substance that's basically, it's usually silicon based, but it allows electrons to move in one direction or the other. So when they get heated on one side, or when the energy level gets high on one side, they just start a flow of electrons, which is all that electricity is. So I like solar panels because I like things without moving parts, because I think they're really cool, but all of them kind of work the same way. And actually, if you think about it, even though we're not talking directly about electrical energy, this is the way your car works as well. You have gasoline. It goes into a cylinder with a piston. The piston, the compression ratio just talks about how hard you push on it and how hard you pull on it. But basically, you atomize the gas. Gas is flammable, and so it creates a little flame front. Piston moves up. You've got volume. It causes something to spin, and your car starts moving down the road. So once again, not ready to go to work for Ford Motor Company with that brief introduction, but it's always about expanding something, turning something, in order to create electricity or mechanical power. So anyway, with a turbine, if you went up to, let's see, my favorite dam in the whole world is, well, maybe not, because I haven't seen Three Gorges Dam in China. But my favorite dam in the United States is the Grand Coulee Dam, just north of Spokane, Washington. And the Grand Coulee Dam produces so much electricity. But basically, any dam, whether it's Hoover Dam or Buffalo Bill Dam, just north of, just west of Cody, all work the same way. You store water up above, the water drops down. There's a penstock that allows the water to flow through. The water spins that magnet/electrical coil. It's not really an electrical coil. It's usually a copper wire coil, and that creates electricity. I just want to see if they have a picture of the generators on here, because that's really what I'm interested in. Let's see. Let's go back to Grand Coulee Dam generators. I just want to see a picture. Okay, there we go. So basically, they all look like this. There's just an exciter that gets everything started. There's something else interesting as well. But basically, this stuff just spins, and electricity, so water flows through, something spins, electricity comes out. And the water comes back out as well. The water's not in the same state. It's at a lower energy state, obviously, but everything else remains the same. Now, if you look at, there's something really interesting at the Buffalo Bill Dam. There are generators like this that function, but there are also non-functional generators in a power plant that is on the National Historic Register. And this seems really strange by modern standards, but when they put in the Buffalo Bill Dam in the early part of the 1900s, it was like 1904, they generated electricity in order to build the dam, but after the dam was built, there was basically no need to generate electricity anymore, so they just shut the power plant in. And so there were very few cities at that time that were electrified, and out here there's nothing. I mean, it was just looked like Badger Basin everywhere. So, so the dam went in mostly for water storage so that people could irrigate. But because the generators there are so old, the ones that don't work right now, The exciter, which actually gets the whole thing started, has a low enough startup that you can actually start it without being on the grid. You can start it just by flowing water through it. Most every generator that's on the United States electrical supply system right now requires so much energy to start that you have to have, they just call it a hot start generator. You have to have the grid on in order for you to put a new generator on. But the ones at Buffalo Bill Dam are actually cold start generators. So they don't work, but it would be an interesting project if somebody wanted to take that on. Or, as I like to mention, in the event of the zombie apocalypse, we may have the ability to generate power here that other people don't have. So, something to keep in mind, because we all need a job for after the zombie apocalypse. So anyway, all right, so getting back to our little easy example here. Not easy, but our little basic example. We have water, steam flowing through this adiabatic turbine. Adiabatic means that Q dot is equal to 0. The inlet conditions of the steam, we have water, and it's at 4 MPa and 500 degrees centigrade, and it is going through at a velocity of 80 meters per second. The exit conditions are 30 kPa, and we have a 92% quality steam, which actually, I'll talk about that in just a moment, and we have a speed of 50 meters per second. So we're slowing it down, and we are sucking off quite a bit of energy in terms of internal energy or enthalpy. The mass flow rate of the steam is 12 kilograms per second. And the questions that we want to answer about this turbine are: determine the change in kinetic energy. Now it says kinetic energy. It might be, there are a couple of different ways to look at it. We could look at kinetic energy in terms of kilojoules, or we could look at kinetic energy per unit mass, which would be in kilojoules per kilogram, or we could look at the rate of change of kinetic energy, which would be in kilojoules per second, which is a kilowatt, right? And this problem really doesn't specify, but if you look at the answer, it's in kilojoules per kilogram, so we're really talking about that to get the same answer as the rest of the problem. The point that I'd like to make is if you go in as steam, most appliances or apparati do better in one phase or the other. If you come out as two-phase steam, you have liquid and steam, you have a tendency to mechanically tear up equipment. So 92% is still going to behave quite a bit like just steam, so you're probably okay. But phase changes within turbines are generally tough to manage from a mechanical point of view. It's not going to make any difference when you look at it on a piece of paper, but if you try to do it in real life, it's going to be a problem. All right, so we know all of our conditions. Let's go back and take a look at some of the equations that we developed, must have an email, yesterday, or the last time we met, is that the summation of mass flow rates in minus the summation of mass flow rates out is equal to the rate of change of mass within the control volume with respect to time. All right, since this is a turbine, we're not accumulating or discharging mass. The mass is just a pass-through, isn't it? So, and we also just have one inlet and one outlet. So when we write the conservation of mass equation, we can just say that the mass flow rate in is equal to the mass flow rate out, and we're actually told what that value is, 12 kilograms per second. All right. Now, as far as the energy, the statement of the first law of thermodynamics, we are also told that Q dot is equal to 0. So we know that negative W dot, which is the power, is equal to, and as I said, we don't have a summation, we just have a single outlet and a single inlet. So we can say M dot times H plus V squared over 2. Now the other thing that you might notice is GZ, there's really no difference in height. If the way that I've drawn the turbine, I've drawn the inlet a little higher than the bottom, than the outlet. However, it's not really a significant factor. If we were taking water at the top of the dam, and we would have to convert that into a potential energy, into velocity, into kinetic energy at the bottom of the dam before we did this problem, but we've already been given the velocities. So we don't have to do that conversion. That happened before our part of the problem. So then once again, we have minus m dot times, and I should put this as out, m dot times h plus v squared over 2 in. And then if we have anything going on, any rate of change of energy within the control volume with respect to time, that would go here. But we don't, do we? All right. So here are our two working equations, one of which is really trivial. So we want to solve for W dot. And what else? We want to solve for the change in kinetic energy. So A, we want delta KE. And we've determined that it's small ke because without a dot, because of the units on the answer. All it's not specified in the problem. The power output is going to be W dot. Okay. Now, this is going to be in kilowatts or megawatts. If it's capital W dot, which according to the answer it is, and then the turbine inlet area, the area on the inlet. It's not asking us for the area on the outlet or the ratio, but we can figure that out as we go. All right, getting down to our problem then. Since this is a negative, we can just switch the side. In other words, we could write the inlet stuff first over here. Minus this stuff, h on the outlet, minus v squared over 2 on the outlet. And we can multiply the whole thing by m dot, because m dot in and m dot out are the same thing. Since I've switched the signs over here, I can switch the signs over here, and this will directly solve for my power. All right, now we have this term. We can get h in and h out from the tables because we're talking about steam. V squared going in was given to us, and v squared over 2 is given as well. So you can use this equation to solve directly for W dot. Now, to solve for delta KE, what's that going to be? Well, it's going to be v squared over 2 on the outlet minus v squared over 2 on the inlet. Now, if you do these conversions, let me just talk about this for a minute. V is in meters per second, so v squared is in meters squared per second squared, isn't it? Well, we want to get the change in kinetic energy in kilojoules per kilogram. Are those two equal to each other? Well, let's find out. What's a kilojoule? It's 10 to the third Newton meters, and that would be times 10, well, let's just say kilogram. We're not going to do it 10 to the third. So then we have 10 to the third. We know that a Newton is a kilogram meter per second squared. We have times meter times kilogram. Kilogram meter per second squared. Just making sure I have everything. Then I have a meter out here, and then I have a kilogram in the bottom. All right, so I find out that that's meter squared per second squared. So what I wanted to show you there is that kilojoule per kilogram is dimensionally equivalent to meter squared per second squared. So that when you solve for this and you come out with an answer of meter squared per second squared, it is indeed a kilojoule per kilogram. Yep?
We have to multiply it by 10 to the third?
It looks like it, doesn't it? Yeah, it looks like we have a factor of 10 to the third.
That goes from the kilojoule.
Exactly. That's exactly right. So what we're really going to get is a joule per kilogram. Or the opposite. We have to multiply it. Let me think about that for a minute, because this will be a huge number. So if we get this, let's do this. Is this a kilojoule per kilogram? So we do have that 10 to the third, right? So what we can say is a kilojoule per kilogram is 10 to the third meters squared per second squared. That's to get our order of magnitude correct. Okay, so if you come out with meters squared per second squared, you have to divide it by 10 to the third to get kilojoules per kilogram. Okay, yeah, that's better, isn't it? All right, let's talk about the area on the inlet. All right, what do we know? We know that the mass flow rate on the inlet is equal to something. And we also know that that's equal to rho V, velocity, times the area on the inlet, which, because we have tabulated data, we can say V on the inlet times the area on the inlet divided by the specific volume at the inlet conditions. So you can pick this up out of the tables. You've been given this value, and you've given this value. So m dot in times v in, little v in, over velocity in will be equal to the area on the inlet. Okay. Now, let's think about units, make sure everything comes out all right. M dot is in kilograms per second. Little v is the inverse, the reciprocal of rho. So this is in meters cubed per kilogram. Divide that by meters per second. So we have kilograms, kilograms. This converts up. We have meters down here, seconds up here when I flip it, seconds. So that'll give us meters squared. So we have dimensional homogeneity with that equation as well, because meters squared is a good unit for area. All right. So 546 is also a homework problem. You can finish that. And I want to do a little something with either a mixing chamber or a heat exchanger. For chemical engineers, mixing chambers can become pretty big deals because they're very much more complicated than this, but the basic idea of mixing components together and balancing the mass of all of those components becomes a pretty big deal. So let's take a look at a problem that's going to help us work with this. All right, let's look at I'd like to have an E problem. All right, 573E. Let's see if it does what we want it to do. We have water at 65 degrees Fahrenheit and 20 psia is heated in a chamber. So we put this into some sort of a chamber, and it's heated in a chamber by mixing it with saturated water vapor at 20 psia. T equals Tsat. And saturated water vapor means X is equal to 100%. Okay? If both streams enter the mixing chamber at the same mass flow rate, so we could call this M dot in 1 and M dot in 2, determine the temperature and the quality of the exiting steam. All right, so what we're saying here is that in this mixing chamber, it's going to, after it becomes full, the mass flow rate out is going to be equal to the sum of the mass flow rates in. So we know then from this, M, summation of mass flow rates in, equals the summation of mass flow rates out, because dmCv dt equals 0. All right, now that's not going to be true until the chamber flows full. So we know that m dot in 1 is equal to m dot in 2. And so when we write this, we can say m in 1 plus m in 2 is equal to m out, because there's only one outlet. Or, since they're equal to each other, 2 m dot in equals m dot out. Okay? So now we know something about this energy and this energy, and we don't know anything about this energy at all. But once this establishes itself, because there's no dmCV/dt, this is going to be a steady flow process. There's no work produced. You know, we really don't know if that is adiabatic or not. But I think we may have to make that assumption. Okay, so if we looked at the basic steady flow equation for our energy, going back to this original form, we have M out, we have M in, we have two different M in streams. We're saying that dmCV/dt is equal to 0. We know that there's no power. This is not expanding or contracting or turning a shaft in any way. But whether it's adiabatic or not is a question. I think we're going to have to assume it's adiabatic in order to work the problem. All right, so for a mixing chamber, it's not a terrible assumption, but I don't really like it that much either. All right, so then all we have to do is to break this down. We have 2m dot, let's just say m in equals m dot, so we don't have to keep writing that over and over again. So here we get Q and W are 0 equals 2 times m times h on the outlet. And there's really nothing going on in terms of the velocity or the potential energy. But that's going to be minus m dot times h1 in, which we know, minus m dot times h2 in. And we can pick both of those up out of the tables because we're talking about steam. And we can solve for h out. All right? Now, what do we know in that particular case? Well, if h out, it tells us in the problem that the steam is, it says determine the quality of the exiting steam. What does that mean? That means it has to be saturated. It's somewhere between two sets of conditions. Okay? So you can determine from h out, you can specify what that's going to be. Now the other part of it is, if you look at this, it's quite likely that the pressure over here is going to be 20 psia. The reason is because there's nowhere on this exit, it's not going to reach equilibrium in the system until it reaches 20 psia, is it? Because both of these streams are at 20. So over here, you can make the assumption, fairly good assumption, that the pressure is going to be 20, and find out what the T is. You actually know then what T is because it's saturated, and then you can use that just to find that value of H here and solve for X. Yes?
Like a sealed chamber?
Yes, and there's a lot of assumptions on this problem, but yeah.
I'm confused on how you can say that it's 20 out if you have two streams of 20 coming in.
Well, if you think about it, inside of the chamber, if they're both coming in at 20, what's going to cause the pressure to dissipate in the chamber? In other words, what's that? That's exactly right. It has to. And so once it starts flowing full, it's going to have to be in mechanical equilibrium. So after it gets past the outlet, it's not going to be at 20 anymore. But at the outlet, it will have to be at 20. So in other words, we're assuming that those two streams are mixing fully within the mixing chamber, and that on the outlet, they're going to be in mechanical equilibrium. not really crazy about this problem. There's an awful lot of assumptions. I don't even believe it's going to be adiabatic, but you have to make that assumption in order for the problem to work. We don't have enough data otherwise. But if you solve for H, then you can go into the table at saturated water at 20 degrees. Then you can solve for X. Does that make sense? What do you think? Yeah.
That's still a little iffy, but I understand.
Yeah, I'm not really crazy about it either, so I have to tell you, it's that bothers me, and also just the fact that there's no heat given. I mean, I'm not convinced this would be an adiabatic process either, so.
Because wouldn't it, like, if it ever tried to get above, like if that was closed, if they closed
Yes.
it off, wouldn't all three of those go up until?
Well, sure. If you closed it off, this is a really good point. If you closed it off, what would happen is mass would accumulate inside of the mixing chamber. I mean, you could build pressure.
The pressure would build up, like.
Exactly.
Equally on the points, right?
That's exactly correct. Because if we're talking about steam, because here we have some sort of hot water, and what we're doing is we're mixing it with steam in order to put it into the two-phase region. That means that in here we have to be between steam and hot water. You know, we're going to be somewhere in that continuum. So if this mixes fully, if we have two-phase, it has to exist at the same temperature, doesn't it? Or same pressure, doesn't it? It's just not possible for it to exist any other way. Still don't like it. But anyway, I started doing it because I wanted English units on it, and maybe I should have gone to an SI problem. But it's okay, it's okay. The basic process of solving here is to find H sub out, and then then you need to have one more variable in order to fix the state. So you have to have either temperature or pressure. So after you find H, then you have T and P, you're going to be able to solve for X. So that's the process. Yes?
And I know you already said
It's
this,
okay.
but how did you say to find H sub out?
Oh,
It
okay.
would be tabulated?
Right, because it's steam, H is in the tables.
Okay.
So you know, do you really know mass flow rate? Not necessarily, but if you look at this equation, there's an m dot in each term, and so they're going to drop out. So you'll be able to find H in 1 and H in 2 because those states are fixed. So then based on this equation, you're going to be able to find a value for H sub out, which is just going to be these two subtracted from each other divided by 2. And then when you have that value, you can take that into the tables at 20 psi for saturated liquid water, saturated, not liquid, saturated two-phase water. And then you can fix, when you find that value, then you can find X using that information. Does that make sense?
Yeah.
Yeah.
You set that equation equals 0 because it's adiabatic, so Q dot is 0 and there's no work.
Right, exactly. And that's basically because a mixing chamber doesn't change volume and it doesn't create work. All it does is just mix things together. So, all right. Very good questions. On a moderately bad problem, I guess. So, it's okay. It's not a terrible problem. Let's take a look at a pipe or duct flow, just real briefly, and I'll set one of those up for you. So here, so far, your 2 homework problems, and you'll have one more. 546, 573E, and now we're going to do a pipe or duct problem. All right, what's the difference between a pipe or a duct? Well, a pipe, in general, has a round diameter, or sometimes they'll have an oval diameter, which actually happens in some big water delivery systems. There's some up by Rogers Meat Processing Plant. Some of the irrigation structures actually have an oval or elliptical cross-section. But a duct is a general cross-section. It can be anything, but generally a duct could be, a pipe is a duct, but you can also have square or rectangular cross-sections as well. These are more typical for transporting things in the vapor phase. Most of the time water, because it's heavy, or any liquid will have either round or elliptical cross sections. And that's the difference. So all pipes are ducts, but ducts ducts are a more general term. Okay, so there's things that are ducts that are not pipes. Exciting. Let's take a look at one. Oh, I should do it. Dang it. All right. Let's see. Um, 589E is really quick, and then that'll actually give me time to work one more problem, which is a charging and discharging process. I don't know if I want to do, I think I already did that. So this will be our last problem. 589 will be our last problem. Okay. 589 says we have water that enters a boiler at 500 psia as a saturated liquid. Okay. That means X equals 0. Goes into the boiler, and it leaves at 600 degrees Fahrenheit at the same pressure. Calculate the heat transfer per unit mass. Okay, that's what a boiler does, is puts heat into the system. Boilers don't create work. They don't generate power. They take hot water or cold water, heat it up, and they put work into it. Then this hot water or steam over here will do the work, whatever needs to be done. I'll heat a building, that sort of thing. And boilers are they're pretty interesting. They're pretty interesting. People go to heat exchangers a lot more, which are a little bit different, but boilers really can do the job for big industrial buildings, especially. All right, so it asks us for Q per unit mass. So we're really solving for little q. And so what are we doing? Well, in the boiler, once again, the dmCV dt, in other words, the rate of change of mass within that boiler is equal to 0. So all we're looking at is Q dot minus W dot equals mass flow rate in times H plus V squared over 2 plus GZ, summation of those, minus summation mass flow rates out times H plus V squared over 2 plus GZ. All right, so here we do not have any work. So we got Q dot, we have a single inlet in and a single inlet out, and the mass flow rate in then has to equal the mass flow rate out. So those are both just equal to m dot. So we get m dot times H in, because velocity, kinetic are not, or velocity and potential are not a big deal, minus H out. We have Q dot here, we do not know m dot. If we take Q dot and we divide it by m dot, we get Q dot is in units of, say, kilojoules per second. Mass flow rate is in kilograms per second. This cancels out, and you're left with kilojoules per kilogram. So Q dot over m dot is little q. And in this case of just the simple case of pipe flow, Q is equal to H in minus H out, which you can pick up out of the tables. That's how much heat you have to add to the boiler in order to make water at 500 psi and 0 quality become superheated steam at 600 degrees Fahrenheit and 500 psia. Okay? So any questions? All right, this is it for chapter 5. These are our last 3 homework problems. So on Tuesday, I won't collect this homework, of course, but Tuesday next week we'll start chapter 6. And we'll do chapter 6 in just a couple of days. It's an introduction into the second law of thermodynamics, but it's chapter 6 is before we really get into the math of it. Chapter 7 is where we'll get into the math of the second law. So do a little math, but not too much. So it's more of a think about it kind of chapter. So, all right, I will post the vodcast. I will post these 3 homework problems, and we will see you guys on Tuesday of next week. Except for Matthew, you're coming to my office at 1. Okay, sounds good.